Okay, good morning, everybody. Day two. So I've just put up on the slides, you saw the rough sequence for day two and the very rough times. I've lengthened the breaks because 10 minutes is not enough time for me to make a coffee and drink it. So I pushed it to 15 minutes. So we're going to continue with part two. We got about halfway through the Tellurium thing yesterday, so I'll continue that. Lucy will talk about SPML, biomodels, and a bit more antimony. Then we'll have some examples to motivate our practice with Tellurium, and that'll be bistability and oscillators. What I'll do is I have slides, and there's code on the slides, but I want to write the code in real time on Colab, so we can work on this together. And then I have a little mini project for you at the end. Okay. Okay. Let's get out of that, and we'll go to it was this one. There you go. Okay. So let me go right to the top because I have to, as I said, Colab tends to forget very easily, and I have to reinstall Tellurium. So that's the first thing I'm going to do. Okay, so exclamation mark pip install Tellurium minus Q. There it goes. It's faster this morning. So that's almost installed. It's almost there. So you'll all have to do this because Colab just forgets. Looks like it's still doing it.
Morning.
There it goes. Morning.
Yeah.
There it goes. So
Okay.
then it says restart the runtime. Okay, let's do that. This is only for Colab, just the way Colab
Hey,
works.
can we talk for a second?
Yep.
Sorry, I needed to mute.
Oh, okay. Was that me or some?
You're good.
Oh, I'm good. Okay. Okay, good. Yeah, this is an overall. And so some quick basics. I'm going to check that I have Tellurium ready. So there's this import Tellurium as TE. I'll run that. Make sure that's okay. That looks good. I can do a final test, I guess, by loading this very simple model. One reaction, S1 to S2. Those of you who like real names, I can put in glucose 6-phosphate to fructose 6-phosphate. There you go. Okay. And to make it, and of course, I know that reaction is actually irreversible. So why not I make it irreversible? By the way, it's important that you keep the exact names for the species. If I do this with a lowercase p, that's incorrect. Okay, so it has to be capital P because it's capital P in the name there. The same goes for here. Now you don't have to initialize all of these because they get set to 0 by default, but it's always good practice to do that. And I've got
Your
another.
parameters do need, your K1 and K2 do need to be initialized because
Yeah, those, and it'll complain, but that
yeah.
was an early trap I found when I was a graduate student and building models. If the tool didn't tell me that the parameters weren't initialized, I would always get problems because didn't realize that the parameters hadn't been initialized, and they were set to 0, and I was getting weird results and I didn't know why. And so now we have the tool. In fact, I can show you. So if I comment that out and run this, it'll complain. Okay. Says global parameter K2 is missing a value. Okay. So that's to protect you. Okay. So I'll put that back, rerun it, and it works. Okay. So this is an equilibration reaction because it's reversible and it's reaching equilibrium here. Okay. Okay. All right, let's go on then, shall we? Let's go to where we did that. I think we got as far as, well, we did the exercise.
You did all the
Did that.
getting the different types of names of stuff.
Oh yeah, we did. Oh, this is the last bit. Yeah, here it was. I think. Yeah, this is it. Yeah. Okay. So, we got to this point. The question here was, how can I change values for parameters? I mean, of course, I can change them here right? I can change the parameters there, but how do I change them afterwards? So let me run this. So that's the simulation on this one. So this is a longish pathway. It has one external species S1 that's fixed and 3 reactions. The last one has an empty sink metabolite, I call, but I don't care so much about that. So and it's not part of the rate law either, so I really don't care. I could name it just like that if I wanted to, but I need to make sure it's fixed, of course. But I'll leave it like that. Okay. So how do I change a parameter? It's actually really easy. Let's change K2 to 3.4. So I'm going to reset the model. That resets the initial conditions for S1 and S2 back to their original values. And then I just change K2 like that. It's as simple as that. So R.K2 equals 3.4. I run it, and you can see I get a slightly different simulation. Okay. So changing values is really simple, and you can change anything like that. I could even change, what was it, S2 to 10, right? I'll get something slightly different. There you go. I get a slightly different one. Although again, you notice that I've obviously got not enough data points here because I can see the straight edges. So let's boost the number of data points to 300, and now I should get a nice smooth curve. Okay, there you go. So you can change anything, any parameter, any variable you want just by doing this. Okay. There is one other little trick I can show you. What happens if? Let me just show you it first. You can do it this way too. And you might be thinking, why would I want to do it this way? So I can actually do it by specifying the name of the parameter as a string. This can be useful when you've written a program where all you have is the string name of the parameter, and you need to change that. Or you're running a simulation where you're going through all the different parameters, and you need to be able to change each parameter in turn, say within a loop. And you can't do it this way because that's specific parameter K2. So within a loop, I can't change this K2 symbol. So the way to change K2, say in a loop, or you have another parameter you want to change each time through the loop, I would use a parameter. In fact, let me give you an example. I think the best thing to do is just give you an example. So first of all, I'm going to get all the parameters, get global parameters IDs. So what I'm going to do is I'm going to comment these out. We're going to do this stage by stage, and I'll print K, right? Okay, so get global parameter IDs simply returns a list containing all the names of the parameters. Okay. So what I can do now is, let's start a list for, actually, let me change that to parameters. Okay. And then I'll go for K in parameters.
Parameters up above there.
Whoops. Parameters. All right. Parameters. Is that right? Let's just show you what this does. So now I've started the beginnings of a list for K in parameters, then printing K. Let's see what that does. Okay, so that just prints K1, K2, K3. So what I'll do now is I can do this. Let's do a reset. Right, I don't need to do the reset up here. Do the reset in the loop. And then I'm going to set that parameter, let's say, to some random number. So let's bring in the random number package. Random, and I think it's, come on, yeah, random.
Yeah. Above one more.
Oh, okay, good. That'll return a number between 0 and 1. Now let's say I wanted a random number though between 0 and 10. All I do is multiply by 10. Okay. So that'll now randomize that parameter K. And now I'll run a simulation. That'll do. And then I'll plot it. Okay. And then let's run it. And so now I should get 3 plots, although they all look Are they all the same? I'm not sure.
Yeah, they're different. The middle
They're
one is
different?
particularly different.
Oh yeah, yeah. See, they're all different, right? So the use of the string form lets you do little tricks like this, okay? But when you're doing a simple model without any loops or anything, you can just go r.k2. That's really easy, okay? But if
One
you
thing
want
I'd
something,
mention
yeah,
about this is that reset is not resetting those Ks because it's reset on its own only resets the species, the floating values, but reset all would reset the Ks as well.
correct, yeah. So yeah, as Lucian said, there's another reset called reset all. What that does, it resets the parameters and the initial species concentrations back to what they were before. And in fact, if I wanted to change one parameter at a time but restore the previous values, I would use reset all. Now what this means is I'm only changing one parameter at a time, and I'm restoring the parameter values back to what they were before I change the next one. So if I ran this, I get something slightly different. Okay. So one thing you might be asking, we're not going to do this now, I'll do this later, is I'd rather not have them all in, 3 different plots. It'd be nice if you could put them all on top of one plot. I'll show you how to do that later, okay? All right. Here's an example. I just thought I'd better show you an example of a rail model. This is what a rail model might look like. This is modeling an enzyme mechanism, okay? And this also highlights how to do bimolecular reactions. So this first reaction is enzyme plus substrate gives enzyme substrate complex, okay? And of course the rate here is this is a mass action law, and a mass action law requires you multiply all the reactants together times whatever rate constant you have. Okay, so it's K1 times E times S. The second reaction is the breakdown of enzyme substrate complex. Now I could have done it like this. Let me comment that out. I could have done it like this, right? And just made it reversible. But I chose to make it explicit like this just to show the separate reactions, okay? And the last reaction is, of course, the enzyme substrate complex breaking up into free enzyme and product. And there's the rate law for that. Then I set up some constants, set up some initial conditions, and I run a simulation, and this is the result we get. In fact, this is a nice little model. It illustrates why we can use Michaelis-Menten equation as an approximation, because you'll notice that at the beginning, there's a very, very fast transition for ES and E, and then everything's relatively constant. And that's what we depend on when we use the Michaelis-Menten equation. We depend on this, the ES in particular, being constant, which it is here. And you also notice that the product formation is constant and the consumption of substrate is constant. Now, of course, eventually we run out of substrate and then everything goes back to where it was before. But during this time, everything, the amount of enzyme complex is constant, and that's why we can use the Michaelis-Menten equation. Okay, so let's do something very different with Tellurium. Okay, so the problem is this: I have a rate law. This is it down here, right? It looks like a more complicated one. In fact, it's a Hill equation. So there's a Vmax, maximal rate, times the substrate to the power of some number n, divided by some Km, some kind of constant, plus s to the power of n. So this is a Hill equation. And the characteristics of a Hill equation is that it has a sigmoid response. And I would like to plot that as a function of s. So I'd like to plot this rate as a function of s. All right, and I'm going to show you how you can use Tellurium to do just function plots. All right, and I'll show you 2 ways to do it. One is relatively easy to understand. The other is a bit more subtle. But let me show you the easy one first. Okay. So my model has a single reaction because I'm going to investigate how this rate J1 is affected by changes in S. Okay. So I've set up my initial values here, and then this is the program that I'm going to use to plot the rate versus S. So I'm gonna set up an RN here so I can change that if I want to later on. I'm going to create two empty lists, X and Y. Okay, so X will go on the X-axis, Y will go on the Y-axis. I'm going to start a loop. Now this loop uses NumPy, and I've imported NumPy up here. I'm also going to use matplotlib. I've imported matplotlib up here. I need NumPy because I need access to this A range. All right. Now the advantage of A range is that it can do fractional ranges. So what we see here is we see the A range has 0 to 5 in steps of 0.1. I couldn't do that with range, okay? So if I were to run this, let's go up here and make a little code. Let me print. I know what's going to happen here because I need to import NumPy because I haven't imported it this morning yet. So if I run this, this is the list I get. So these are all the values I get from this A range. Starts at 0, goes up to 4.9, goes up in steps of 0.1, okay? So this is going to form my x-axis. All right. So I'm going to start a list using this A range, and S is going to be assigned that value in A range each time I go around the for loop. And I'm going to assign RS, i.e. this substrate level in the model, to S. Okay. Now S is going to be my x-axis, so I'm going to append S to my X list, which is currently empty. And I'm going to append S. The other thing I'm going to do is I'm going to append the rate, the reaction rate through J1. Now, when I ask for J1, Tellurium will automatically compute that, given the current set of values for the model, okay? So because I assigned S to a different value, it'll compute the rate at that value. And so then this goes round and round and round, collecting X and Y values, appending them to the list and so on. Then all I have to do is just plot it. So for matplotlib, you just give the X and the Y list. I'm going to do some labeling, add an X-axis label, X and Y-axis label, and then let's run it to show you what you get, and this is what I get. So this is actually a way of using Tellurium to look at a particular rate law. Maybe you found a rate law in the literature and you want to see what it looks like. You can use this sort of thing to plot that rate law. And just to show you that it works, let's change the Hill coefficient, say, to 1. So in other words, it shouldn't be sigmoid at this point, and it isn't, okay? Now, you may think, well, it's not going far enough. I need to go beyond 5. Well, in that case, let's just increase this to 10, the upper limit, and now it goes to 10, okay? I can change the Hill coefficient and see how it goes. It's starting to show sigmoidicity. Let's go crazy, put 20, shall we? See what it does. And now, oh, look, it's an extremely sharp, almost a step response. But you notice there are some edges here because I haven't got enough points. So let's put more points in. Now it should be nice and smooth. And there's nice and smooth. Okay. Now, although it's going too far up, really, because all the action is down here. So let's take it to 4 instead of 10. I can run that. Okay, that looks a bit better. Okay. So this is a quick way. Well, maybe not quick. You have to write all this, but it's one way to plot a rate law or any function. Like you can put any function you want in there, actually. So you can use Tellurium as a general function plotter if you want. Now, somebody, I don't know who did this, but somebody came up with this trick. It's a quicker way of doing it, fewer lines, but it might take a little bit to understand. This here does the same thing as the one above, and it gives me the same plot. We're sort of abusing Tellurium here in some way, but because if you think about it, we could, when we do a simulation, time moves forward, okay? Well, we could use that as our X variable, all right? Although it's time, we could use it as our X variable. And that's what we're doing here. So what I'm doing here is I have time. This is a variable that's given to us for free by Tellurium. And I'm going to assign S, the substrate level, to time. Now that sounds a bit odd, but I'm going to interpret this time as a substrate concentration, not time, simply because time moves forward, just like the x-axis moves forward. Okay. Now this colon equals is very important. That means that this line here, line 6, gets executed all the time during the simulation. So during the simulation, S will get updated all the time. Okay. I have the same line as before. This is the same rate law, initialize some things, but now I do something different. I now run a simulation. Okay, so I'm not doing, not building a list up and appending stuff. I'm doing a simulation because I can interpret the time in this simulation, 0 to 5, as the concentration of X because of this line. And I don't want to plot time itself this time, though. I want to plot S. So I'm going to use a selection list to plot S versus or S on the x-axis and then J1 on the y-axis. I'll do a plot. Plot takes arguments too. It'll let me add a label. I'll do that. And if I run it, I get the same plot. So this is a bit of a trick. Maybe not as obvious as the other one, but I remember somebody gave this to me a few years ago. I don't remember who it was. It might have been Lucian, of course. Anyway, there's a little trick you can do. Okay, so this is the bit now where we start talking about, well, I'd like to overlay lots of plots. So I'm doing a whole lot of simulations, and I want to put the simulations one on top of the other, okay? So remember up here, we had what, separate ones. I don't want that because it's too difficult to look at. I want them all on top of each other, okay? So a good example would be the Hill coefficient problem. So at the moment, I change the Hill coefficient individually and I re-plot it. But wouldn't it be nice if I could change n in a loop and then plot everything on top of each other onto one plot? Okay, so that's what we'll do here. And then okay, spoil the fun. There's the answer itself. But this is how I did it. I'm going to use this trick just because there's less code involved, but this will work with this as well. All right. So what I'm going to do is I'm going to set this up as well. So here I'm setting up S equals time. This is the rate law. I'm initializing n to 1 at the beginning. And then I'm going to start a loop. And this loop is going to be done 5 times. In this loop, I'm going to run a simulation. I'm going to collect the data. And now I'm going to use a new function. Now, you could do this using just matplotlib, but it's more complicated, so I didn't want to show you that. But you can do this with matplotlib, and I may have an example later on where you do that. But I'm going to use this quicker one. Tellurium has a thing called plot array. And what this does, it treats it'll take an array M, which comes from simulate. And it treats the first column as the x-axis and all other columns as the y-axis. Okay. Let me come back to all this in a minute. Then I'm going to increment the Hill coefficient, and then I'm going to go back again. All right. Now, one thing that's important here is there's an argument called show, and I'm telling it that show is false. And what that means is it won't show the plot. So it'll do this loop 5 times, but not show the plot. In fact, what it's doing, it's accumulating the plots. And then right at the end, when I'm ready, I call plot array again, but this time I say show is true. All right. I have to give it M as well. It doesn't use M in this case, but you need to give it anyway. And I just say show is true, and it'll just then dump the plot out. Okay, and this is what you see down below. Now there are a couple of things here. Let me show you what happens if I leave this reset color cycle out. If I run this, I just get blues. Okay, it's using the same color every time. To make it use different colors each time, I tell it to reset the color cycle, okay, to false. I don't reset the color each time. Just use the next color you have, The other thing I'm doing is I'm adding a label, right? So I can get a legend, right? And I'm constructing that. You notice it's labels, not label, and also it's in a list. That's because M may contain more than one Y column. It may contain multiple Y columns, and I want separate labels for each column. Now here we've only got one Y column, and so I only have one thing in the list, okay? And this list is constructed by having a string, n equals, plus the value of the Hill coefficient. And I have to convert that into a string because it's a number, okay? And I can then add them together. And I get the label down here, right? The other thing I'm doing is make sure the legend is outside is true. Actually, I don't know if that seems to be working, actually. The legend is not outside. Let's see what happens if I don't have that. Oh, it means, I think it means the legend should not be on top of the plot itself, on top of the lines, okay? So that'll ensure that the legend is outside is not on the lines themselves. All right, so this is how you can do overlay plot. Now I can go a bit crazy and put 50 in here. Let's say put that as 0.05 and then run this and you'll see you get, it takes, yeah, okay. You get that and the legend is a bit crazy, okay? But I think you get the idea, okay? So that's how you can do overlays, all right? Oh yeah, and of course I got to take that back to 0.5. Now you could have just one here, so it goes from 1, 2, 3, 4. That's okay too. All right, there it goes. You get 1, 2, 3, 4, 5, and you get the same thing. So that can be quite useful. Oh yeah, this is the same thing now using matplotlib. So instead of using plot array and this trick with time, I'm just using it perhaps the most basic way you can, and maybe it's an easier one to understand. So I just have the model here, and I have to have two loops now. I have to have an inner loop and an outer loop. The outer loop is going to change n, the Hill coefficient. So it's going to change. I've got a loop here, 1, 2, 3, 4, 8. All right. The inner loop has to then plot that particular line. All right. So I have to have two loops, one to plot the line, one to change the Hill coefficient. Okay. Now at the beginning of the outer loop, I need to initialize the x and y axes lists to nothing. I need to set the current n, and then I start the inner loop. That's going to collect the x and y data for the plot, okay? And I have an A range here to help me vary S. Once I've collected everything, I now do a plot, okay? And then once that's done, it goes around and starts the next value for the Hill coefficient, initializes the x and y list to empty, and then starts again, right? So it does this. So in fact, this loop, there's quite a few times these loops run. And then right at the end, I set up the y and x and y labels, and I also make sure the legend gets plotted, all right? Now, one thing about plot is plot won't plot until either the cell is complete or I say show. So if I were to put show here, right, if I did plot show, it would ruin everything because now it would plot each one individually. See, they're all separate, okay? And for some reason it's gone a bit weird on me. There you go. All right, so they're all separate. So you don't want to use show. It'll basically hold on to the plot until the very end, and then there's an implicit show that's called right at the end. And that's why then we end up with all the separate ones, okay? All right, and now what happens if I wanted to do, I don't want to plot a rate. I've got an actual model I want to look at. So here it is, I have a simple model, 3 steps. And I want to know how this model responds as I change K1. So K1 is the rate constant in the first reaction. I want to know how the model responds as I change K1. This is similar to what I did before, but before we had separate plots, okay? So now what I'm going to use plot array here. All right. And it saves me for having simplifies things a little bit. But I'm going to set up K1 as 0.1. I'm going to have a loop going through over five times. This is really important. I need to reset the model, the initial conditions for S1, S2 back to where they were at the beginning. Then I'm going to run a simulation, but all I want is time in S1. Then I'm going to use this plot array, and I'm going to tell it, don't show the plot at this point. Don't reset the colors. Let's have a legend as well. Then I'm going to increment K1. Then right at the end, I'm going to tell it, now show the plot. So if I run this, I get this plot. So this shows me how, I mean, like how S1, that should be S1 here, how S1 changes with K. That should be actually K. Let me see, how can I, oh, label should be, that should be K. There we go. And then I guess K1, and I should put the Y label in as well. Let's put the Y label in as S1. Okay, let me run that. That'll be a bit better then. Okay, there you go. So now I've got K1 on the x-axis and S1 on the y-axis. All right, so I got 1, 2, 3, 4, 5. 5 different simulations at 5 different K values. All right. I want to emphasize this reset here because that's really, really important for this particular simulation. If I don't have reset, let's take it out and I run, you'll get something that looks very different. What's happening here is the first one here is okay, but what's happening is the second one is starting with the S value from where it left off. The third one is starting where the S value was last, where it left off previously. The fourth one, the S value starts at where the one was previously as well. So that's why it slowly works its way up like this. I don't want that. I wanted to start the S value, S1 value. Actually, the S1 value is at 0. I'll just emphasize that in a sec. I wanted to start at 0 for S1 every time. So to do that, I need to do a reset. And then when I run it, now it looks better. All the S values are starting from 0. Okay. Okay. So yeah, how are we doing?
No, you're doing fine. Just people have noticed that there is no purple line in there, and I think it's because it's because the last plot array thing goes back to blue again and then plots it twice, basically.
Oh, you're right. That's why I should do.
So I think if you just comment that out entirely or reset, yeah.
Well, if I comment that out,
something? Do you need like plot show or something?
yeah, because let me comment that out, right? Show you.
It's not going to do anything.
Actually, it does do something.
It does do something, yeah. Like after the
does.
end of the cell.
At the end of the cell, it just
yeah.
Okay. Just to show you, if I did leave that in, I don't think I'll get another blue. Yeah, I'm getting a brown. Although now the legend.
And now it's not on the legend because it didn't get its label and stuff.
Oh yeah, it didn't get its label. Yeah, we won't do that then. Let's get rid of that. Get rid of that. The show will happen once it leaves the cell. Okay.
Yeah.
Yeah, that's much better. Oh, thank you. Well spotted. Okay, yeah, that's much better. Yeah. Now, as before, I can go a little bit crazy here. I can do 50 here and point, say, 02. I can have lots and lots and lots. Takes a while to do this. There you go. All right, but that's not very practical. Okay, so if I notice there's a cycling 1, 2, 3, it goes to 10 colors and cycles back maybe or something. Maybe 12 colors, then it cycles back. So we won't do 5 because that's a bit too crazy. We'll just do we won't do 50. We'll just do 5. Okay. X label should be time instead of K1. Indeed. It's too early in the morning. There you go. Time. Thank you very much. Any other questions coming on that we need to answer?
I think we got them as they came.
Got them. Yeah, that's right. Why is there no purple? Good question. Okay. All right, let's go on to a different topic. You'll notice that all these lines are approaching what we call steady state, okay? So if I ran long enough, let's go up to 30 maybe here. If I ran long enough, they sort of level off, right? I think they're still changing, so let's do 60. Okay. Now maybe they've leveled off now, right? Be nice to find out what the rates of change are here, right? To see if it has reached steady state or not. So I can go get rates. Remember we did this one yesterday, get rates of change. That, all the rates of change, of which there are 2 of them, should be close to 0. Why is it not close to 0? That is odd. Mistake have I made here? I don't quite understand why it's not at 0.
One of them's at 0 and the other one isn't. So something. Are we plotting S1, but is S2 still changing or something? Or I
Yes,
don't know.
that is odd. Doesn't make any sense, that.
Can you get the rates of change labels? Like what?
Yeah, I'll do that as well. It should correspond to the floating.
Okay, yeah.
I'm not quite understand why it's 1 there. Must be something to do with this loop. That is
Oh,
strange.
yeah. It was you changed K at the end. You changed K1 and then didn't simulate, but K is different,
yeah,
so
yeah,
it's
yeah,
it
yeah,
would
yeah,
be
yeah, yeah, yeah,
it
yeah.
would suddenly be changing
Yeah,
again.
in fact, yeah, that should really be moved up to here probably. And we can set that to 0. If I run this, I still get the steady state. Now we'll ask for our get rates, or get rates of change. Oops, sorry. Get rates of change. Now there's 0.
There
Yeah,
you
thanks
go.
a lot. Great, thanks for that. So yeah, sometimes you have to do a bit of debugging and be careful what's happening. What happened here, those of you may didn't catch that, I was changing K1 right at the end. And so when I changed it at the end and it left the loop, of course, with the new K, the system is in a different state now. It's not really at steady state at that K. And it was telling me that the rates of change were not 0. But if I ensure that the K is set before I'd run the simulation, so that now after the simulation, it's definitely at steady state for that K, I will get 0 rates of change. So it's 10 to the minus 11, 10 to the minus 7, okay? Now, you notice that I had to steadily increase the time here, right? They say I start at 10, and I want to get the steady state. You're saying, yeah, that's not a steady state. Let's go up a bit more, 50. Yeah, well, that may be at steady state, but maybe it isn't. Let's go to 500 to make sure, okay? There are times when you may never be sure. And you may have to go to very high times to actually reach the final steady state. So instead of doing this, if you want to find the steady state, instead of doing it this way, we have a shortcut for you. Okay, so this is, we have a shortcut for you to compute the steady state. So a very simplistic way is to run the simulation for a long time like this. So I got this model here. I'm going to run it for 30,000 time points. Right, and then I'm going to pick the last one, 29,999. If I run this, right, it's out of bounds. Is it really? 30,000. Oh, I've only got 100. Sorry, that's correct. So it's 99. Yeah, I've only got 100 points though, but so I need to look at 99. And if I look at 99, this now is the last point during the simulation. Okay, it's 2. No, 3.
It's 30,000. It's a time, yeah.
Oh yeah, that's 30,000. Thank you. 30,000, 2.5 and 1.785. That's the two. These are the two lines here. There is a better way though of finding the steady state than doing it this way. This can be unreliable if you're not careful. The way to do it, of course, is to call the method called steady state. I guess we weren't consistent in this case. We should have called this get steady state, but never mind. It's called steady
It
state.
actually, it's called steady state because it changes the state of the model to the steady state, right? It's like simulate. It actually like moves the model to that state, right?
Yeah,
It
yeah,
doesn't just get it. It
yeah.
changes
That
things.
makes
Yeah.
sense. That makes sense. Oh
Yeah.
yeah, that makes a lot of sense now. Well, I'm happier now. Yeah, so I can just call that and it'll compute the steady state immediately, right? Uses a special algorithm to do that. So I'm going to call it and I'm going to ask it to print out S2 and S3. Let's just do that for a moment. Let's just look at that, run this. And there is the steady state, if you can see it, 2.5, 1.785, right? Now we have another one, another call that also computes the steady state, but this one is different in that it labels, it comes back as an array, and it labels the array for you, so you know what's what. So if I call get steady state values named array, it actually returns this little thing here, right? So it's an array, but it's labeled it, so you know which is which. So it says that S2 has a steady state level of 2.5 and S3 has a steady state level of 1.78571. But I can convince you that this really is the steady state by asking for get the rates of change. Okay. If I get the rates of change, they both should be 0 or close to 0. Oh, they are 0. There you go. Dead on 0. Now, they're not always dead on 0. There's sometimes a very, very small number, like 10 to the minus 16 or something. But that's the steady state. Okay. All right. Yeah, so the system now is in steady state. So S2 and S3 are now different from what they were. So so just to emphasize, the initial conditions are S2 equals 0 and S3 equals 0, okay? They were both at 0 at the beginning. They're not at 0 anymore. They're at 2.5 and 1.78.
You could even copy your print line before, put it in before line 14 also. Copy line 15 before line 14.
Oh, yeah.
Just
Oops. Yeah, that's good.
yeah.
Let's get rid of these two for now. Run. Yeah, before 0, 0, after 2.5, 1.785. And just to convince you it really is steady state, I can also do a simulation. Of course, nothing will happen because we're at steady state. So it's going to look a very dull plot, okay? So don't get too excited. Told you, very dull plot. All right. So it really is at steady state. Nothing is changing. Okay. All right.
Someone had a question about, or just saying if it changes the system to the steady state, it will probably be useful for loops testing perturbations around the steady state. And that's
yes, definitely.
That's true. Yeah, that's absolutely
definitely. True. If I'm going to show you that shortly, actually,
Okay.
yeah, I'll show you what we can. There's something we can do with this with events. I'll show you. Okay, so that's a nice quick way of. Okay, somebody else, can I get the time? There is no time. It's a completely different calculation. It's based on an optimization algorithm. If any of you know Newton-Raphson algorithm, it's a root finding algorithm. What we're essentially doing here is we're solving this system, f of s equals 0. So it's a completely different problem. It's like solving a quadratic equation, right? You're looking for the roots of the equation. In this case, the equations are two differential equations which we set to 0 and then solve for that. So just to emphasize this, I'll just, let me see, it's k1 times s1 minus k2 times s2. That's the differential equation for s1, and this is the differential equation that Tellurium derives for the second one. Now, what Tellurium does, it works out these differential equations, then sets them to 0, and says, okay, they're set to 0. Now find me S1 and S2. That's consistent with them being equal to 0. All right, so it basically sets both of them to 0 and then solve. And I mean, in this case, it's a linear equation, so it's very easy to do. But it solves this using a root finder. So there's no time really. I mean, it'll be milliseconds, I guess, but there's no actual simulation time. All right. Okay, good.
You might want to comment out those lines again before leaving it there.
Yeah, just might as well.
Yeah, sure.
Okay. So I seem to jump to another topic here, but I'm going to come back to steady states again. Okay. I wonder how many of you are familiar with phase plots, phase portraits, that kind of thing. If you're a dynamics person, they're very important to you. So a phase plot is simply where I plot one of the variables against one of the variables. So I'm not plotting it against time. They are moving in time, but I'm plotting the two variables together as they change in time. And I'm going to show you, so we've done some extremely dull models up to this point. And let me show you a little bit more of an exciting model. Let's show you an oscillator model. This is the first oscillator model. We'll do a lot more on oscillators later this morning. But this is an oscillator model. It's from, I call it the Heinrich model. It's from his 1977 review. That's a really good review, actually. I highly recommend it. It's actually, the reference is dated 1978, but it's actually marked 1977 on the review itself. So it's actually 1978, January the 1st. So there was a transition there and it got mixed up. Anyway, the title is Metabolic Regulation and Mathematical Models. It's a great paper. Quite a long paper. Some bits are maybe very theoretical, but there's a lot of general stuff in there too. And in one case, they have this model. Okay, let me move this over here. Let me move that there so it's all lined. They have this model. All right. And this model has 4 steps. It has 2 variables, y1 and y2. The first step has a constant rate, p0, right? So think of that as a rate constant. I just call it p0. This is from another exercise I do with my students. So that's why the symbols are different. But that's really a rate constant. And it's coming in at a constant rate, right? There's nothing that can stop it. And the constant rate is 7. So y1 is being made at a constant rate of 7. Y1, however, also degrades at a rate that's directly proportional to the amount of Y1. So you can think of this as making the first step reversible, actually. This is effectively what it's doing. All right. Then we have Y1 gets converted to Y2. I'll come back to this in a minute. And then Y2 gets degraded out at a rate P6, Y2 times P6, all right? This bit here is the important bit. What this bit is actually comes in 2 parts. There's P1Y1 times 1, and there's P1Y1 times P4 times Y2 to the 4. What we have here is we have a normal rate, right? So if I got rid of that, that just looks like a normal mass action, right? Nothing special about that. But when I combine it with this extra bit, what I have here is a positive feedback, because this rate is affected by the product itself. So when there's more product, the rate goes up. Now, initially, when there's no product, I say there's no Y2, the rate is given by this. As product gets made, this piece starts to light up, but because it's to a power, it's a very strong signal. And it causes the rate to increase at a very rapid rate. Okay, and that is a destabilizing influence. But when you couple it with these 2 steps and these 2 steps, that can stabilize this positive feedback. And we'll come back to this later in the morning, more what's going on here, but that's essentially what's happening. And it can destabilize it so that it So that it sort of collapses. But then when it collapses, the destabilization stops and it starts to go up again. So if I run this, you'll get some nice oscillations, okay, in Y1 and Y2, right? And you notice there's sort of two sort of behaviors here. There's Y1, which is, well, sort of sinusoid, but it's got a very sharp peak down there. And then we have the orange one, Y2, which is a very sharp peak, and then a much slower transition back to the sharp peak again, okay? So you've sort of got two different time scales here, and this is very characteristic of oscillators that use positive feedback. Now, what dynamics people like to do, though, is they like to plot phase plots or phase portraits. And the way to do that is simply to plot Y1 versus Y2. So although this is time down here, I'm now going to plot Y1 versus Y2. Even though Y1 and Y2 are evolving in time, you'll see how they change in time together, right, as we plot it. And the easy way to plot it, and probably guess how I'm going to do it, I'm just going to have a selection list, and I'm just going to ask it to plot Y1 and Y2. And if I do that, I get my phase portrait. Those of you who've done dynamical systems will recognize this. This is a sort of off bifurcation limit cycle. And so it makes it very easy to do these kinds of phase portraits. One thing to bear in mind is, you notice I got a very large number of data points here. If you just pick the usual 100, it doesn't look good at all. There just simply aren't enough points, all right? In fact, you have to go quite high, actually. If I go to, let's say, 2,000, then you get a nice smooth curve, all right? So those of you who do dynamics and who do phase portraits, it's very easy to do phase portraits. Just to show you what I can do with this, I can change. I know that the injection rate P0 can affect the oscillators. So if I drop this to 3, I think, and rerun it, see, nothing happens. Let's push it up a bit to 4. Nothing happens. 5. Oh, it's starting to twist. 5.5. Yeah, it's starting to twist a bit more. 6. Now at the moment, this is it's actually reaching a steady state, all right? It's not actually oscillating, but you can see there's a bit of a twist in the trajectory. If I go to 6.5, oh, it's already done it. Okay, so I have to drop down to 6.3. Oh, yeah, let's do one more then. 4. Okay, you see that. So it's a nice way to look at how a system behaves under different values of a rate constant. Now, one thing I haven't got here, but it's nice to do with matplotlib. You can construct a grid of plots using something called subplots. So I could have a loop, and I could vary P0, and I could have a grid of these plots to show the evolution of the system as I change P0. All right. Okay, so that's a phase plot. And you'll notice here that in this case, the trajectories seem to converge on a point. In fact, let me increase the time so you can see the convergence a bit more. Yeah, it seems to converge to the steady state, right? It's orbiting in. If I were just to show you what this looks like, if I added time, you'll see what's happening probably. It's basically a damped oscillation, okay? So in phase space, a damped oscillation looks like a spiral that spirals in on itself, right? And it's, of course, it's reaching a steady state, right? There it is, that center point here. That's a steady state. Now, because it converges to a steady state, we call this steady state a stable steady state, right? It's stable because the system wants to evolve towards it. In some sense, the system is getting, in fact, this is exactly what's happening. The system is getting pulled into that point. All right. Okay. So let's look at a little bit more detail at the steady state. All right. So this is just another one that does a time simulation. Gives me this. I've got three values here, three three state variables, S2, S3, and S4. So I've got three plots here. I can get to the steady state immediately, as we said before, by calling R steady state. All right. Print them out. Here are the steady state values. Okay. So that's good. Actually, let me see. Hold on a minute. This is not what I wanted to show. Okay. In that case, they're missing. So let me add them. Right. Okay. I'm gonna add lib now, so I'm gonna add this code. So I'm gonna take this. Actually, I'm gonna take. Actually, I'm gonna start with this one. I'm gonna take this one, run it. Oops, run. Okay. And what I'm gonna do is I'm just gonna plot one of them. Let's plot S2. Okay. No, let's plot S3. All right. And it seems to be reaching some kind of steady state. Let's push it on a bit further. 40. Okay, that's good. Actually, no, let's go to 80. Now, I want to know if this state is stable. It looks stable, right? One way to check if it's stable is to make a perturbation to it. So if I were to change it, we could then observe to see what happens to it, all right? So let's do that. Let's add an event at time greater than 60. I'll go S2 equals S2 times 2. So I'm going to double. Well, that's a bit excessive. Let's increase it by 20%. Okay, S2. So time 60 at around here. Yeah, time 50 actually. That's too far in. Time 50 around out here. I'll increase S2. If I do that, you notice there's a spike. It goes up, and then it decays back down. Actually, maybe I will increase that a bit more. Okay, you see it coming back down. That's characteristic of a stable steady state. Okay, but any perturbations I make decay. If I can go a bit further, I can create another event. This time I'll decrease S2. So I'll decrease it at let's say 100 further up in time. So if I do that, now you see, well, there's not enough points. Let's push the number of points up so it looks nicer. Now you see two perturbations, one positive, one negative. And in both cases, the system returns to the same state, and we call this a stable state. Okay. Now I'll have a lot more to say about this in the talk after Lucian, so I'll leave that at that for you to think about. Okay. This is a nice little application of events. Okay, especially if you want to, if any of you teach this kind of stuff, this is a nice way to show that the system is stable. So we've sort of come to the end, I think, of that. I just want to mention one other thing before we leave. So I've written a bunch of utilities in a package called TEUtils. This is for my own purpose, but it's available to everybody. And I keep expanding it. You can get it by doing a pip install TEUtils. I'll just show you some things that it can do that might be useful to you. One thing it has is a lot more plotting options. So yeah, the two things it's got really are a lot more plotting options. And it also lets you generate random models, right? Random networks. And I use this for for checking things out and so on. But you can generate a lot of random networks. I can generate a random network where things are just connect to each other randomly, or I can generate a linear chain, right? That has random parameter values, and I can set the, where is it? The length. So let's say I can generate a linear chain of 10 steps. All right. And before I run the simulations, let me show you what that model looks like. I can print the network, and I can run it. Oh, I got to import it. That's always a good idea. Right, now I can run it. And that's what the model it generates. So it generates this random linear chain, okay? So x0 to S1, S1 to S2, 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 S2 to S3, and so on. It puts boundary species at the front and the end, and it puts in this sort of a reversible mass action rate law. It also has this little E at the front. It sort of represents enzyme. And then they're all initialized down here to just random values, okay? And I can do this as many times as I want, and I'll get a different set of random values, all right? So with that, I can now I can load this model into antimony, run a simulation, and see what I get. There you go. That's your random model, all right? In this case, it's just a linear chain. I could do the random network, sorry. This time it takes, what does it do? The maximum number of species you want in the network and the maximum number of reactions you want. Now, those 20 species can be connected to any other species just randomly, okay? And this is where things can get more interesting. For example, this is a bad one because one of them is going off to infinity. I can run this again, get a different random model. Two of them are going off to infinity. No, that one's going off to infinity. And you can keep running. Oh, this one is a stable one. Look at that. Right? Nothing goes off to infinity. And so I use this sometimes for testing or just for getting random models and doing, you can generate a population of random models and look at statistics and so on. So that can be useful. The other thing, a couple of plotting methods that are available in the utilities is that you get from plotting. You can plot all the floating species. So for this, let's do this model, shall we? So I'll take this, right, and I'll put it in here, right?
You may, your current
Okay.
network is the one that, like, if you do run that again, you're gonna get a new one.
Ooh, yeah, I wanna actually
You want
do
to
this
keep
one.
that one, like
I
save it
want
somewhere or
to
something.
keep that one. Hold on, yes, because that's a nice one. If I run this, it'll show me the distribution of all the species. And although it looked quite nice, it turns out it's fairly skewed. So there's a lot of S5, S9, and S18, but nothing much of anything else. So in this case, let's actually generate a new network. We see what it comes up with. That's a bit more evenly distributed. The other thing I can do is I can plot all the fluxes, right? If I run this one, I'll get the fluxes for that previous model and so on. And if you're really old-fashioned, I got a couple of ASCII plots, all right? They just use characters to plot. So this plots an ASCII concentration bar where the number of asterisks gives you the concentration, right? And it's because it's put on its side. So the species are down here, S1, S2, S3, and so on to S9. Okay. All right. One last thing I want to show you. So I have a lot of fun with ChatGPT, as a lot of us maybe have, and Claude 3. And I just thought, just for the fun of it, let's see what I can get ChatGPT to do. I mean, we've used ChatGPT a lot to see how much it can do with modeling. It's not bad. It's quite good. It knows a lot about antimony and SPML and Tellurium. One thing I thought I'd ask it to do was to fit a model. Now we haven't done fitting yet. That'll be tomorrow. But often what you'll have are parameters in your model that these Ks. Okay. You don't know what they are, right? But you do have data on S1, S2, and S3. And so what you want to do is you want to adjust the Ks, the parameters, so that you get that they match, so that the model matches the changes in S1, S2, and S3 that you got, say, from an experiment. So that's called model calibration, model fitting. And there's a bunch of packages online that let you do that. It's an optimization method. Depending on what package you use, they can be a bit laborious to write. So I thought, hey, ChatGPT, how about you write some code to fit a model for me? Okay. And I can't believe it, but it actually did it, and it did it correctly. It did it in a way I wouldn't have thought about. Well, I mean, I wouldn't have done it this way, but that's the way it did it, but it worked. So it wrote all this data, all this code for me. I also asked it to generate synthetic data for me to fit to, because I don't have the experimental data, right? I have this, I have this fictitious model, right? As I told it the kind of model I wanted. I wanted two reaction steps, S1, S2, and S3. I asked it generate some synthetic experimental data for me, and I want you to fit the model to that synthetic experimental data. And it said, of course, certainly, here's the answer. And amazingly, it did it. So it imports everything. It's importing a SciPy optimize, which is what it's doing the fitting with. It created the model. I didn't give it the model. I just vaguely told it what model I wanted. It created the antimony model. It did all this. It even generated all the synthetic data. Not only that, it added noise to the synthetic data to make it realistic. It then defined the objective function. You'll learn more about this tomorrow, okay? But then it defined the objective function, which I need for the fitting. It provided an initial guess, and then it ran the fit. Not only that, it provided a whole bunch of nice plotting code to produce a nice looking result. And that's what it gave me. So the red, the blue are the synthetic data. This is your quote unquote experimental data. And the orange is the fit, which of course looks pretty good to me. Okay. So that was quite remarkable. So you can do quite a lot with if you have access to ChatGPT. This is the cheap one. This is the free one. I'm not using I don't have a subscription. All right. This is the free one. It can be an assistant, and I emphasize assistant. Obviously, you would look through this to make sure it looks okay, all right? Or you'd try to look through it anyway to make sure it looks okay. I mean, I was suspicious of this bit, so I read up about the objective function for SciPy, and it was correct. It was doing the right thing. But otherwise, it did a remarkable job of doing this. And presumably, I could make this model as large as I like. I could even provide it with the model initially. I tell it, don't make up your own model. Here is a model in antimony. And you could also provide it with the experimental data as an Excel spreadsheet, and it'll just go ahead and do the fit. All right. So anyway, quite remarkable. Yes, certainly. That's right from a comment. It does that all the time. Any last questions on that? Because I'm done, I think.
There was one earlier question about if you ask Roadrunner to get a steady state and there were multiple steady states, what will it do?
Very good question. And I'm not going to spoil the fun because I'm going to tell you that after Lucian does his talk. We're going to answer that exact question probably after the break, okay?
Probably after the break, yeah.
So yeah, good question. Where are we here? Okay, so we're
done with our first 25-minute section.
Yeah, that only took 45 minutes. Good.
It only took 28 minutes, so that's good.
So what do you want to do just SPML and biomodels? Then we'll have the break, and then you can continue with the antimony.
And then do antimony after that?
Yeah.
Sure. The biomodels might be a little shorter.
Yeah. Okay. I'll hand that over to you.
Sure.
Yeah. If there's any questions, one was, do I need to download Roadrunner? No, it comes free. You get it free with Tellurium.
Yeah.
In fact, it's Roadrunner that does all the simulations for you. Okay. No problem. Okay. There's never a stupid question.
No. Oh, it's showing the wrong one.
Oh, can we pause for a moment? I'm going to stop
Sure.
recording and start a new segment.